Hello Simio users. Today I will be reviewing a supply chain example model where neural networks are used to route orders. In the model, warehouses create orders to replenish products in their inventories. When replenishment orders are generated, they must be routed to the factory, which minimizes the order's make span. Neural networks are a machine learning algorithm applied in many domains, including computer vision and natural language processing. In Simio, neural networks use a supervised learning approach, where training data is collected and used to train the neural network. As shown on this slide, Simio supports neural networks for regression, where a collection of input values is used to predict an output value. For instance, using a neural network to predict the processing time at a server given a specific worker, a specific product, and a day of the week. The supply chain model uses an object-oriented approach, where functionality is split into different objects. This approach can be useful for modeling complex systems because it enables the user to break down their problems into smaller sections. The key objects for this example, from left to right, are the demand generators, the warehouses, and the factories. The demand generators create new orders and submit the orders to their warehouse. Once the order is complete, it is shipped back to the demand generator object and destroyed. When the orders arrive at the warehouse, they are fulfilled from the warehouse's inventory, which is modeled using material elements. Looking into the warehouse object definition, we can see that the fulfillment process is modeled as a single server. Orders for each product are fulfilled in series, but are not processed until the required quantity of each material is available. The order entity will wait at material order combiner 1 until all requested products have been retrieved. Then, the order is shipped back to the demand generator. The warehouse's material elements use a min-max replenishment policy. When the inventory level of a particular product reaches its reorder point, a replenishment order is generated. The replenishment entity exits the warehouse and must then be routed to a factory. This is the decision we will use neural networks to solve. Once the replenishment order arrives at the selected factory, the factory will manufacture the individual products. The capacity of each factory varies, so the amount of time to process a given order will vary by factory. Once the order is complete, it is shipped back to the warehouse. When the replenishment order arrives at the warehouse, the inventory level of that product will increase. The objective of this example is to minimize the make span of the replenishment orders by routing the orders to the factory with the smallest predicted make span. Therefore, the decision point occurs at the output of each warehouse object when each entity is determining its destination. When building a supply chain model, it is important to account for the fact that each factory will likely be entirely different. It could have different routings, different machines, or different ways of moving material. Therefore, this neural network approach uses one neural network per factory to estimate the make span of a given order if that order is routed to that factory. This allows each neural network model to be trained on separate data. If one factory changes, only the neural network model for that factory must be retrained. To incorporate neural network models into the factories, Start by adding a neural network model to each factory object definition. Neural network models can be added by selecting the Data tab and opening the Neural Network Models view. The neural network model stores the model's parameters as well as the model's training data. After defining the neural network model, a neural network element must also be added. The neural network element defines the neural network's inputs and outputs, as well as the events which will cause the neural network to collect training data. After creating the neural network element, define the input and output data used to train the neural network model. In this case, I am using input data associated with the factory's workload, such as the number of products waiting to be processed in the factory and the number of products that need to be manufactured for the incoming order. The type of product in the incoming order is also included. Selecting the input data is a key step in designing a neural network model and will likely be entirely different for each use case. For instance, if this factory used many subcomponents to manufacture each product, it might make sense to include inventory information like the quantity in stock of each subcomponent or how long ago the last replenishment order was submitted. For the output value, the expression calculates the make span in working hours. Because including off-shift time adds variability to the neural network's training data, this expression is used to standardize the make span so that it only includes working hours based on this factory's schedule. Reducing variability in training data often makes it easier for the neural network to learn and sometimes results in a neural network with superior accuracy. Once the neural network element and neural network model are configured, data must be collected to train the neural network model. A key element of this approach is that each object in the supply chain model that contains a neural network must be able to run individually so it can collect input data. This is because an object instance will not collect training data. Therefore, each factory definition must have its training data collected individually. Data can be collected in the neural network models view using Simio's data generation features. To start, select each neural network and determine the number of training data records to be stored in its training data repository. Then open the Generate Training Data ribbon and click the Select Neural Network Models dropdown. Ensure that the neural network model, which should collect data, is selected. After setting up the neural networks, click the Run button to begin the data collection process. Simio will automatically run replications of your model until the number of records in each neural network's training data repository equals the neural network's maximum records limit. There is not a set requirement for the quantity of training data required to train a neural network, but often large datasets will improve a neural network model's accuracy. If more data is required for your neural network, the neural network's maximum records limit can be increased and more data can be collected. Simio will automatically change the random number seed for each run so the records in your training data repository are not duplicated. Once an appropriate quantity of training data is collected, the neural network can be trained using Simio's built-in trainer. To train the neural network model, select it in the Neural Network Models view and click Train. This will open Simio's Neural Network Training dialog, where the training parameters can be adjusted. Click Start Training to begin the training process. Once the training is complete, click Save and Close to save the trained model. Training a neural network is oftentimes an iterative process where, depending on the error in the neural network model, the inputs might need to be adjusted and the data recollected to improve the quality of the neural network. An alternative to training the neural network model in Simio is to export the training data and train a neural network in another program such as TensorFlow or PyTorch. Then, the trained model can be converted to an ONNX file, also called an ONNX file, and imported into Simio. Because Simio allows users to import ONNX files, machine learning algorithms other than neural networks can also be used in Simio. For instance, machine learning algorithms from scikit-learn, a popular machine learning package written in Python, can be exported to the ONNX format and imported into Simio. Once the neural network in each model is trained, an instance of each factory definition can be placed in the supply chain model. To reference a different neural network for each potential destination, this model uses a table-based approach. The routing destinations table defines the possible destinations of a replenishment order as well as the neural network element associated with each destination. To use this table, each warehouse's output node specifies an entity destination type of select from list and a node list name of routing destinations.node. This means that the transfer node's routing group will choose a destination from the table and assign that destination to the entity. The selection goal is then specified as smallest value, and the selection expression references the neural network column of the routing destinations table. When the transfer node routes an entity, it invokes each factory's neural network to determine the predicted makespan of this order, then selects the factory with the smallest predicted makespan. Because the neural network standardizes each facility's current state into a makespan for the given order, any facility can be included in this approach if its order's makespans can be estimated. Now that the neural networks are trained and integrated in the supply chain model, the impact of this approach can be evaluated using an experiment. This experiment tests the effect of two controls, routing type and inter-arrival time. The routing type control specifies how the replenishment orders are assigned to factories. The random routing type causes replenishment orders to be assigned to a factory at random, and the fewest orders routing type causes replenishment orders to be assigned to the factory with the fewest orders currently in progress. The neural network routing type still assigns replenishment orders to the factory where the order has the smallest predicted makespan. The second control, inter-arrival time, specifies the distribution of the time between arrivals at each demand generator. This experiment includes both low and high demand scenarios for each routing type. The responses used in this experiment are fulfilled demand, average quantity of orders in queue, and average order time in system. Fulfilled demand is the total number of products fulfilled from both warehouses. Average quantity of orders in queue is the average quantity of orders waiting to be processed at the warehouses. And average order time in system is the average time it takes an order to be fulfilled, starting from the time the order is created. Each scenario has 20 replications, and each replication was run for 4 weeks. Examining the design grid, it appears that the neural network routing type performed better than the fewest orders routing type in both the high and low demand scenarios. When compared to the fewest orders routing type, the neural network routing type scenarios fulfilled more demand, decreased the average order time in system, and reduced the average number of orders waiting to be processed at the warehouses. Viewing the box and whisker plots for each of the responses yields a clearer picture of the impact of the neural network routing. For fulfilled demand, in addition to increasing the average fulfilled demand, we can see that the neural network appears to reduce the variability of the fulfilled demand. We can also confirm that the difference in average fulfilled demand between the fewest orders and the neural network routing is significant for both the high and the low demand scenarios. For the average order time in system, we can see that there is more overlap in the ranges of these distributions in both the high demand scenarios and the low demand scenarios. However, there is still no overlap in the confidence intervals for the means of these distributions. Therefore, we can conclude that the neural network, on average, decreases the order time in system in both the high demand scenarios and the low demand scenarios. For the average quantity of orders in Q, we see again that although there is overlap in the range of these distributions, the confidence intervals of the distribution means do not overlap. Therefore, we can conclude that the neural network reduces the quantity of orders in the system on average. It also appears that the neural network reduces variability in the average quantity of orders in Q, especially in the low demand scenarios. Based on these results, we can conclude that implementing a neural network routing approach provided significant improvements to the system's key performance indicators. This example demonstrates a neural network's ability to standardize the state of a facility into a predicted makespan, allowing Simio to make intelligent decisions within a complex system. Simio's neural network features also equip users to collect data, and the use of the ONNX format allows users to apply many types of machine learning models beyond neural networks. The ONNX format provides new and unique opportunities to experiment with machine learning in your Simio models. Although some may be experienced with machine learning techniques or the ONNX format, this information might be new to others. Therefore, the Simio user forum might be a good place to get Simio-centric answers to your machine learning questions from other Simio users. I encourage everyone interested in diving into these neural network features to get involved on the Simio user forum, which is available to all Simio insiders and can be found via our website. I recently posted a document containing information about how to export or convert your machine learning models and other machine learning packages into the ONNX format. If this is something that might interest you, you can find this document on the forum. If you are not yet a Simio insider and need additional information about Simio or our neural network features, please reach out to support@simio.com. Thank you for watching this presentation, and we hope you enjoy using these new features to incorporate machine learning techniques into your Simio models.
All right, good morning, Rylan. Thanks for that thorough presentation. I know I certainly learned a lot, considering these are the new features for Simio, so I know we have a lot of questions from the audience on more detail about how it all works. I think we can start off with one that's a little bit lighter, if you will. Could you discuss maybe some other use cases that you could see that could benefit from the neural network feature that you just described?
Sure. One use case that I've heard that I think is particularly interesting is using a neural network to predict a processing time,
Mm-hmm.
but not just predict it, but actually use the predicted processing time as the processing time at a server. For instance, if you have different shifts with different manpower or different types of workers, or maybe even weather affects
Mm-hmm.
your process, you could bundle all of these features, throw it into a neural network, and use that to predict the processing time and actually use that in your model.
That's great. That's great. Yeah, one that I was discussing as well with a colleague was maybe even transportation times between sites, kind of using that as a predictive measure for that as well. So if you had the right inputs for it. So okay. One question that came here too is the model that you presented, is that available for any of the users to access and view?
Not yet. If there's
Okay.
interest, I'm sure we can make that work. We actually used a feature that is will recently be released or soon be released in an upcoming sprint, to actually put together this model. So as soon as that's available, we can then actually make the model available.
Okay. Great. Great. Okay, so these next set of questions really kind of dive into the neural network, the feature, and how it works. So let's just kind of start at the top here. Is the neural network model always assured to be the optimal network model? If so, like what parameter does it optimize to determine the best model possible?
It's a great question. The neural network is not assured to be the optimal neural network model. I don't think that's the case with really any machine learning model. In this case, neural networks are trying to optimize a loss function, but I'm sure people are familiar with a local versus a global minima. But an issue with any machine learning model is that sometimes a model will get stuck during training, and it'll get stuck in a local minima. It won't actually find or the global minimum. So we've added a couple features in our neural network trainer to avoid that. Momentum is a very common technique used with stochastic gradient descent, where you kind of want to keep momentum going. Think of a ball rolling down a hill, right? You don't want it to get stuck in the local minimum. You want it to get
Hmm.
all the way down to the bottom of the hill. That's what momentum will do for you. So we have some features in there that will kind of help you get to an absolute minimum, but you're certainly not guaranteed to get to that global minimum. The parameters that we're using in this case, a neural network optimizes a loss function. For
Hmm.
loss, we're using mean squared error. So we take the output of your model and calculate the MSE, and then back propagate that back through the network and assign all the little weights and biases. And we do that many, many times until we can get as close as possible to that global minimum.
Okay. Okay. I think that's a good transition into this next question. So it says here, usually to validate a model, you need training data to train the model and testing data to report how well the model does, typically in residual error, as you just mentioned. How do we, I guess this should say, how do we understand how good our model does on the testing data?
This is a great question. Validation is extraordinarily important when for any machine learning model, neural networks
Hmm.
included. What we do is we separate your entire training data repository. We actually take out a fraction of the training records, and some of those are used for validation, and some of those are used for testing. And the difference here is we use the training data to train your neural network. We actually feed those records into the neural network, get the error back, propagate that back through the network. The validation data is used for things like early stopping that actually affect the outcome of the model. So if your model stops training and we look at the validation data and we say, hey, the model's not training anymore on that validation data, we want to stop your model. We don't want it to overfit. The testing data, we don't actually use that during the training. That is completely separate from any part of the training process. We use that exclusively to evaluate the performance of your model. So that's how we understand how good the model we've trained is. We separate the training data to be sure we get an unbiased estimate of how well your model is performing.
Great. Okay. Um, here's another one here on just some more of the feature itself. Does the neural network feature automatically decide how many artificial neurons to use, or will it decide how many to use if it's trained, or as it's trained? Sorry.
The feature does not decide how many artificial neurons to use. We leave that up to the user to
Okay.
define the architecture for their network. We start with a good default, which is a number of neurons equal to the number of inputs to your neural network, and for a lot of you know basic problems, that is perfectly sufficient. You can then scale your network out according to your problem. I would also add that because we've added Onyx support, you can do things, and I've done this myself. I think this is well worthwhile. Is put together a script in TensorFlow, and if you want to try out, hundreds of different architectures, just write a script to do it for you and import it into Simio. The way that we've uh, allowed people to integrate all kinds of machine learning models into our software, I think is going to be huge for us moving forward.
Agreed. Agreed. Great. Thank you for that. We got another one here. Is overfitting ever a concern when the neural network model is created and trained?
Absolutely. Overfitting occurs when the model hyper specializes on the training data set that it's provided,
Mm.
and the validation data set, or the testing data set, which is just part of the entire problem, right? It's only part of the population. Of course, sometimes the network will hyperfixate on the training data and kind of memorize that without having a generalized understanding of the entire population. And so how we avoid that is we added early stopping functionality, which is a very common solution to this problem, where as soon as the trainer identifies that your loss is not improving or getting smaller, right? There's As soon as
Hmm.
you're not reducing the amount of error in your neural network, we stop training for you, and you can of course tweak those parameters to suit your problem, but that way you won't be overfitting your models.
Nice. Okay. Thank you for that. I think we got time for a couple of more here. There's one that says, why use a neural network over machine learning models such as a random forest is?
Uh, Random forests are, I'm not an expert. Again, I've of course done a lot with neural networks, not as much with
Hmm.
random forests. Um, but generally speaking, some algorithms perform better on some problems than others.
Hmm.
Personally, whenever I'm working on a data science type problem, I try out a bunch of models and just see what works best. Again, this is another great reason to include that we have supported Onyx is if you decide that, hey, I think this algorithm would work better, a random forest or an SVM, whatever that may be, you can actually train that in scikit-learn. And a lot of these models that are not neural networks, they're just other type of machine learning models, can then be exported out into an Onyx format and imported into Simio. And I've actually tried that out. I think it was with a random forest just to verify that some of this functionality worked as it should, and I got really great results. Getting all of these other types of algorithms to work. So if you want more information on that, I highly recommend checking out the document I posted to the forum.
Great. Okay. Thank you. I think you mentioned a little bit this in the presentation, but I guess maybe we can just reiterate here with this last question. How would you leverage the neural network model routing that you sorry the neural network routing that you modeled in Simio to inform business decisions on routing processes?
I so something that interests me in this type of arena is trying to decide how the neural network decides how the neural network decides make span or predicts make span for a certain factory. If I
Hmm.
can learn that, oh, actually, a large queue of this specific type of part causes the neural network to identify that this is a problem, I can then focus in on that part of the process and say, oh, okay, there's an issue here in this queue or this section of the factory. So that's the type of mindset that I would go into it is okay. So the neural network has identified this as an issue. What's causing the problem, and then, of course, take on a more industrial engineering perspective to that issue.
Right. Okay. So the neural network would give you more of that optimal look to then determine what in real life is different from that, or giving a comparison tool.
Exactly.
Great. Okay. Well, thanks again, Rylan, for the great presentation. I think everyone get a lot of it out of it from the neural network feature. So I see a lot of use cases in this for the future, and really appreciate your time here at Simio.
Thank you, Ryan.
This concludes this presentation. Please click on the back button to access the next presentation.